Mr. McBrien. This is TEJ3M, the monitor. So today we're going to talk about not just monitors, we're going to talk about video cards, we're going to talk about ergonomics. The Ontario government would like for us to be able to talk about these things, specifically video cards, and talking about the ergonomics of video, including avoiding eye strain. The monitor, we can first and foremost think of it as the most common output device. The monitor, the display, the screen, the visual display unit, if you want to be verbose. It is essentially an electronic visual display for computers. Now, originally computer monitors were used for data processing and television receivers were used for entertainment. This distinction has really begun to change, and for this reason, computer monitor quality has increased greatly. Now, the quality of the picture we see on the monitor depends not just on the monitor quality itself, but upon the video controller and upon the settings that we choose inside the operating system. And again, from the 1980s onwards, computers began to be used not just for data, but also for entertainment. And that means that graphics quality is a significant concern and an area of active development. So let's talk a little bit about that development. The underlying technology of graphic display remains an area of evolution. We're going to talk about the cathode ray tube briefly just because it's such an interesting technology. Talk about LCD monitors, LED monitors, and additional technology is being developed almost yearly. The monitor isn't the only thing that creates that image. The video card is important as well. So this ancient looking device is an example of a monochrome monitor. And this is what computers looked like before the mid-1980s. You had a cathode ray tube screen and a single color. Green was common. You could see crazy orange as well. And a massive innovation was the idea of a grayscale monitor like this Macintosh. And these allowed you to have shades of gray, which was, for the time, a very rich visual image. So these early grayscale monitors would give you 16 different shades of gray. Amazing technology. Now, by the mid-1980s, we were starting to see colors, and these color monitors were just like we're going to see the cathode ray tube work, except they had 3 electron beams instead of 1. And we'll talk about those electron beams in a second. Those 3 guns gave us additive colors, red, green, and blue. The beams themselves, though, it's important to realize, didn't have a color associated with them. Instead, the pixels had the colors. So you had ones with red phosphors, green phosphors, and blue phosphors, and arranged them in a triangle. And when the beam of the gun hits these, the phosphors light up and can combine into the colors we want. So, using various intensities then, we can have varying intensities of red, green, and blue to give us the colors that we wish to have, all of the colors of the rainbow. Now we'll call this group of dots a pixel, and the pixel is very important to our understanding of how an image is displayed. By the way, this is straight out of science class, but mixing colors, we can see equal amounts of red, green, and blue will give us white. If we have increased intensity of red and green over blue, we'll tend towards yellow. And similarly, we can achieve other colors by mixing these things together. Now, the cathode ray tube has very interesting aspects of physics, and in fact was very important to us understanding how the atom is put together. And this is part of why we're still looking at it. Even though it's hard to find a cathode ray tube in a computer lab these days. So the CRT works by having electrons travel through a vacuum sealed container, and they travel from the negatively charged cathode to the positively charged anode. Because the electrons are negatively charged, this is the push that moves them from the cathode to the anode, but it is also that charge is an attribute we can exploit to aim the ray, aim the beam. And this is what makes it so useful for purposes of generating an image. The energy of that electron is given up when it strikes the anode, and by putting that phosphor coating at the anode, it'll emit light. It gives up that energy as light. But because it's negatively charged, we can aim it with a magnetic field. So we can use a magnetic field to put it where we need it to be. And so here's a little cartoon of a cathode ray tube with our fluorescent screen on the right-hand side. And so our fluorescent screen here, we have our cathode negatively charged, and we pull the electrons off of the cathode, they strike the fluorescent screen, and this gives us our image. Again, the magnetic field allows us to take the negatively charged electrons and deflect them, aim them. And here's a little mock-up of how this thing works. So essentially, the image is created by this screen and the phosphor dots on the screen emitting light based on the striking of it by the electron beam. And the image is generated by having the beam scan repeatedly across. And so it goes left to right, top to bottom, and refreshes each one of these phosphor dots in this kind of zigzag pattern. And the faster, of course, it scans, the quicker the refresh rate and the less flicker we see in the screen. Now, the cathode ray tube has a bunch of advantages to it. We can control the brightness very much by controlling the current. We can produce lots of brilliant colors with great contrast. Another advantage of the cathode ray tubes is that they're free. You often see them sitting on the side of the road with signs on them saying, hey, feel free, take this thing away because I don't need it anymore. However, the CRT has disadvantages. If you've ever had to move one, you know they're big and they're heavy. They use lots and lots of power. They're high voltage devices. And they have, that tube is made of glass with vacuum inside. Not an ideal situation for terms of durability and safety. And because of the high current flow and high voltages, we have electromagnetic fields emitted by them. So they're not really good for living cells. The constant refreshing of those monitors can also result in headaches and fatigue if you're in front of them for long periods of time. Did I mention that they're heavy and big? So we've seen the CRTs largely discontinued then. Instead, we've moved towards flat screen monitors, and we're going to contrast two types of these over the next few slides. So liquid crystal display monitors use a flat panel, and they take advantage of the light modulating properties of liquid crystals. Liquid crystals don't emit light. They in fact block it. So let's dig into the LCD history for a few seconds, and then we can talk about how we can use them as well. In fact, they're more than a century old, the technology of liquid crystals. And RCA made the first liquid crystal display back in 1968, so they've been around for a long time. By 1997, manufacturers began to offer full-size LCD monitors, and this was at least in part pushed forward by the notebook computer market, people wanting laptop computers. LCDs are very cool because they're lightweight, they have sharp pictures, again bright images, and the screens are flat. They're also fairly energy efficient. So they have lots of great aspects to them. However, they have some disadvantages. The pixels will wear out eventually, leaving black spots on the displays. They have slow response times. And you can't mess around with the resolution display too easily. This can be an advantage or a disadvantage. The viewing angle on these things is fairly limited. And if you're working on the South Pole, you may find you have trouble with cold weather. Let's talk briefly about monitor specifications. We evaluate monitors based on their size, their resolution, the refresh rate, and something called dot pitch. So let's unpack each one of these in turn. Resolution is the number of pixels you see on your screen. So it's a reflection of the sharpness and clarity of an image. We typically express the resolution in terms of a matrix. So we'll say things like the resolution of the monitor is 640 by 480. This means that it's 640 pixels horizontally and 480 pixels vertically. I'll leave you to do the mathematics of how many pixels this is in total. Usually the resolution is determined by the video controller. Monitors can operate at different resolutions, and you can see some examples of these layouts here. As the resolution increases, the image on the screen gets smaller. So if you're seeing icons in Windows get smaller and smaller, this is because the resolution has been set very high. And within Windows and other operating systems, you can modify the resolution how you would like to. Now, there are some basic standards for resolution. So VGA is 640 by 480, Super VGA being 800 by 600, and 1024 by 768. Today, nearly all color monitors can go to things like 4K, where we have even higher resolution. But resolution isn't the only parameter associated with monitors. Refresh rate can be very important. This is the number of times per second the device can write each pixel onto the screen. And so this is important when things on the screen change very quickly, when there's action. So we measure this in hertz or cycles per second. And this means that if the monitor refresh rate is 100 hertz, it's refreshing each pixel 100 times each second. And maybe you're already aware of what the refresh rate of your eye is. Well, this is extremely pertinent in this situation. And you can actually modify the refresh rate as well. Dot pitch is the distance between the same color dots. Ranges typically on monitors between 0.15 and 0.4 millimeters. Obviously, the smaller that is, the finer the picture is. We want to see numbers less than 0.22 millimeters. So if we look at a given screen, if we can take out a microscope and look at it, a pixel would be the triangle of these three dots, and the dot pitch is the distance between the center of the same color. So red to red, or blue to blue, or green to green. If you're good with geometry, you'll realize that that should be the same number for given colors. Now, how do we communicate resolution then? We communicate resolution in pixels. Higher is better. We'll sometimes talk about dot pitch as well, in which case lower is better. But if we consider the screen at the Rogers Center, for example, the dot pitch is a very large number there, even though it's a very high resolution monitor. And if we look at the image from a reasonable distance, even though the dot pitch would lead you to believe that it's a terrible picture, the resolution is excellent. By the way, 4K resolution, I alluded to this earlier, that's 3840 by 2160. But we talked about LCD, we didn't talk about LED monitors. Remember that the liquid crystal display itself does not produce light. Every LCD screen, every screen that uses LCD technology has to have a light behind it. The type of backlighting is the differentiation between an LED and an LCD monitor. So they both involve liquid crystal blocking of the light. The difference is what provides the backlighting. In LCD, the backlighting is with cold cathode fluorescent tubes. In LED, that's provided by individual LEDs. So the good news about an LED backlighting system, modern monitors, is that they use considerably less power than those old LCD monitors. Okay, let's talk about the video cards. IBM introduced the first video card in 1981, right around, if you're keeping track, when they introduced the BIOS. And they call it the monochrome display adapter. Gave us text-only displays of green or white text on a black screen. Now, since 1981, these have been enhanced a great deal, adding more RAM, adding cooling, and faster processing. So here's a sort of anatomy of the video card. We have the motherboard connection on the right-hand side. Most modern video cards have a processor fan to cool off the GPU, as well as a heatsink, and you have onboard memory to take the heavy lifting away from the basic computer. So what does the video card actually do, though? Well, if you did the math when I gave you the standard resolution, you would have realized that for things like 4K, you have more than 1 million pixels. And the computer has to decide what to do with each and every one of those pixels in order to create an image. So there's a lot of binary data that has to be evaluated and turned into instructions for given pixels. If a computer doesn't have graphics capability built into the motherboard, that translation takes place in a graphics card. So, I alluded to this, the CPU sends information about the image that it would like to see to the graphics card. The graphics card decides how to use the pixels on the screen to create this image. Then it sends that information to the monitor through a given cable. And it can even render three-dimensional images. Now, to accomplish this big task, it has its own processor unit on board called a GPU. And this does essentially a lot of geometric calculations for graphics rendering. And this results in less congestion on the system bus, reduces the workload for the CPU, essentially allows the computer to do the thinking, and it does the displaying. Now, all of this has a cost, so all these calculations, modern GPUs will have as many or more transistors than an average CPU. And for this reason, we've got lots of waste heat that has to be taken care of. Similarly, they need to have a lot of RAM in order to store the information for the images. So a good video card has lots of its own memory known as video RAM or VRAM. And this capacity may be from hundreds of megabytes to 8 gigabytes or more. Now, there are various video connections available. I included some of the timelines for this. S-Video invented back in 1979, believe it or not. VGA in 1987 on the right-hand side there. DVI 1999, HDMI 2002, DisplayPort 2006. VGA invented more than 3 decades ago now, still remains in use in many places. Certainly for computers, this is an amazing longevity of technology. So the reasons why VGA ain't great, though, it does allow for electrical noise and some image distortion and some sampling errors. However, whether or not you can actually see any of those things depends on what video quality you're starting with, whether you've got a great monitor, and whether you've got good eyesight. Speaking of good eyesight, it's important to think in terms of ergonomics when we're talking about monitors. We want to try to avoid eye strain, and for this reason we want to choose a good quality monitor, place the monitor at least a meter away from you, center the screen just below eye level. Make sure that there's no reflected light, and practice the 20-20-20 rule. What's that? Well, to avoid eye strain, every 20 minutes we want to take a 20-second break, focus our eyes on something that's far away. So look at the window, see if you can spot a cardinal or something like this. Focus your eyes away. If you lock your eyes on something 1 meter away for long periods of time, you will start to impair your eyesight. Okay, are those the only visual display options? Monitors and their resolution? No. over the last decade or so, people have started to reevaluate video display. So in virtual reality, we have a situation where the user's vision is restricted just to the monitor, and it becomes an input-output device in the sense of it senses what the user is doing at the same time. Augmented reality is where the computer actually attempts to superimpose its output on top of real world inputs, supplementing what the user is seeing. All right, key ideas then from today. Video technology is an area of active development. There's lots of things going on, lots of new technologies coming out all the time. LED monitors are energy efficient because the backlighting is provided by cold LED bulbs. Key attributes of your monitor: the refresh rate and the resolution. Refresh rate in hertz, resolution in pixels. Video cards are important to video performance. They provide onboard memory and processing. And repetitive stress issues can be reduced by proper positioning of your monitor and the 20-20-20 rule. So, your homework: please continue your build. Go ahead and get your monitor set up, and for sure, you want to play around with your resolution settings on your monitor once your build is in place. You can read more about the cathode ray tube in the references given. And if you want to see something interesting, try a simple calculation. And this will give you some insights into the importance of a video card. Look up what Super VGA resolution is. Consider 24-bit color and 120 hertz refresh rate. Can you calculate how many bits per second this is? Go ahead and give that a try, and I think you may find the result rather surprising. Thanks very much. Have a great night.